It is a well-known fact that today, Mars is a very cold and dry place. Whereas the planet once had a thicker atmosphere that allowed for warmer temperatures and liquid water on its surface, the vast majority of water there today consists of ice that is located in the polar regions. But for some time, scientists have speculated that there may be plenty of water in subsurface ice deposits. If true, this water could be accessed by future crewed missions and even colonization efforts, serving as a source of rocket fuel and drinking water. Unfortunately, a new study led by scientists from the Smithsonian Institution indicates that the subsurface region beneath Meridiani Planum could be ice-free. Though this may seem like bad news, the study could help point the way towards accessible areas of water ice on Mars. This study, titled Radar Sounder Evidence of Thick, Porous Sediments in Meridiani Planum and Implications for Ice-Filled Deposits on Mars, recently appeared in the Geophysical Research Letters. Led by Dr. Thomas R. Waters, the senior scientist with the Center for Earth and Planetary Studies at the Smithsonian Institution, the team examined data collected by the ESA's Mars Express mission in the Meridiani Planum region. Artists' impression of a global view of Mars, centered on the Meridiani Planum region. Credit Air and Space Museum Smithsonian Institution. Despite being one of the most intensely explored regions on Mars, particularly by missions like the Opportunity rover, the subsurface structure of Meridiani Planum has remained largely unknown. To remedy this, the science team led by Dr. Waters examined data that had been collected by the Mars Advanced Radar for Subsurface and Ionospheric Sounding (MARSIS) instrument aboard the ESA's Mars Express orbiter. Developed by researchers at the University of Rome in partnership with NASA's Jet Propulsion Laboratory and with the help of private contractors, this device used low-frequency radio pulses to study Mars' ionosphere, atmosphere, surface, and interior structure. The way these pulses penetrated into certain materials and were reflected back to the orbiter was then used to determine the bulk density and compositions of those materials. After examining the Meridiani Planum region, the Mars Express probe obtained readings that indicated that the subsurface area had a relatively low dielectric constant. In the past, these kinds of readings have been interpreted as being due to the presence of pure water ice. And in this case, the readings seem to indicate that the subsurface was made up of porous rock that was filled with water ice. However, with the help of newly derived compaction models for Mars, the team concluded that these signals could be the result of ice-free, porous, wind-blown sand aka Aeolian sands. They further theorized that the Meridiani Planum region, which is characterized by some rather unique physiographic and hydrologic features, could have provided an ideal sediment trap for these kinds of sands. Artists' impression of the Mars Express rover, showing radar returns from its MARSIS instrument. Credit as Anasaghpulka Smithsonian. The relatively low gravity and the cold, dry climate that has dominated Mars for billions of years may have allowed thick Aeolian sand deposits to remain porous and only weakly indurated, they concluded. Minimally compacted sedimentary deposits may offer a possible explanation for other non-polar region units with low apparent bulk dielectric constants. As Waters also indicated in a Smithsonian press statement, it's very revealing that the low dielectric constant of the Meridiani Planum deposits can be explained without invoking pore-filling ice. Our results suggest that caution should be exercised in attributing non-polar deposits on Mars with low dielectric constants to the presence of water ice. On its face, this would seem like bad news to those who were hoping that the equatorial regions on Mars might contain vast deposits of accessible water ice. It has been argued that when crewed missions to Mars begin, this ice could be accessed in order to supply water for surface habitats. In addition, ice that didn't need to come from there could also be used to manufacture hydrazine fuel for return missions. This would reduce travel times and the cost of mounting missions to Mars considerably, since the spacecraft would not need to carry enough fuel for the entire journey, and would therefore be smaller and faster. In the event that human beings establish a colony on Mars someday, these same subsurface deposits could also be used for drinking, sanitation, and irrigation water. A subsurface view of Miyamoto crater in Meridiani Planum from the MARSIS radar sounder. Credit as Anasaghpulka Smithsonian. As such, this study, which indicates that low dielectric constants could be due to something other than the presence of water ice, places a bit of a damper on these plans. However, understood in context, it provides scientists with a means of locating subsurface ice. Rather than ruling out the presence of subsurface ice away from the polar regions entirely, it could actually help point the way to much-needed deposits. One can only hope that these regions are not confined to the polar regions of the planet, which would be far more difficult to access. If future missions and fingers crossed permanent outposts are forced to pump in their water, it would be far more economical to from underground sources, rather than bringing it in all the way from the polar ice caps. Further reading Smithsonian NASM, Geophysical Research Letters featured, Mars, Mars Express, Marsis, Meridiani Planum, Opportunity Rover, Subsurface Water on Mars, Water on Mars.